If you live in the Sun Belt, you know the dread of opening your utility bill in July. The air conditioner is running nonstop, and you're paying absolute top dollar for peak electricity. Getting solar panels seems like the obvious defense. The sun is blazing, so you should be generating maximum power, right? The irony is, solar panels actually hate the heat. As the temperature rises, their efficiency drops, and they actively throttle their own output. This creates a gap between the marketing and reality. You pay for a system rated at 400 watts per panel, but step outside on a 105-degree afternoon, check your monitoring app, and you'll likely see those panels generating closer to 320 watts. To close that gap and get the power you paid for, you have to look past the bold nameplate wattage printed on the brochure. You need to understand the thermal physics happening on your roof. That 400-watt rating comes from standard test conditions, or STC. Manufacturers determine that number in a climate-controlled laboratory set to exactly 77 degrees Fahrenheit. But your roof is not a laboratory. Under the direct radiation of a desert sun, a dark panel absorbs heat rapidly. The actual operating temperature of that hardware can easily climb to between 150 and 180 degrees. This line graph shows exactly how panels respond to that environment, using a metric called the temperature coefficient. It measures the specific percentage of power a panel loses for every single degree the temperature rises above that 77-degree lab standard. As the ambient air climbs toward a typical summer afternoon high of 115 degrees, the power output for a standard panel plummets. If you ignore the temperature coefficient when buying your system, you are selecting a panel that is destined to throttle itself right when your air conditioning needs it most. For years, the baseline standard for residential solar has been P-type PERC technology. It is the most common option offered by volume installers. PERC panels are affordable upfront, but they have a high temperature coefficient, typically losing around 0.38% of their power per degree. On a hot desert day, that results in a 15 to 20% loss of your total system power. To solve this thermal problem, manufacturers developed advanced N-type cell structures, specifically TOPCon and HJT, or heterojunction solar panels. This bar chart compares the power loss across these technologies when your roof hits 150 degrees. HJT and TOPCon panels feature much lower temperature coefficients, ranging from -0.24 to -0.29%. They bleed significantly less power. By the end of a July billing cycle, an HJT system generates 8 to 12% more electricity than PERC, right when rates peak. Upgrading to these heat-hardened panels does mean paying a premium. You can expect to add between $1,500 and $3,000 to the total cost of an 8-kilowatt installation. In the Sun Belt, that premium is a required investment to prevent your return on investment from eroding every time a heat wave hits. Choosing the right hardware sets the potential for the system, but the physical installation determines whether those panels can actually reach it. A common error in high heat zones is flush mounting the panels directly against the shingles to make them less noticeable. This diagram shows the problem with flush mounting. It chokes off ventilation, trapping heat underneath and baking the hardware. The fix is using rail mounts with elevated brackets, creating a 4 to 6 inch air gap so wind can passively cool the silicon. There is a visual trade-off here. The panels will sit higher off the roof deck and be more visible from the street. But the aesthetic gain of a flush mount isn't worth the power loss. Even the most expensive, heat-resistant panels will fail to meet their ratings if they are starved of airflow. The panels collect the energy, but your inverter, the electronic brain of the system, actually converts it into the AC power your house uses. A frequent mistake is mounting a large, centralized string inverter on a south or west-facing exterior wall where it faces the full force of the afternoon sun. In direct sunlight, the metal heatsink on that inverter can hit 165 degrees, causing the system to actively limit its output. This is a process called clipping, and it can even cause the inverter to shut down entirely to protect its internal circuits. This blueprint highlights the two thermally safe zones for your conversion hardware. First, you can place a string inverter on a shaded north wall, or you can use microinverters, which sit natively in the shade provided by the elevated roof panels. Microinverters add to the upfront cost and put more electronics on your roof, but they operate independently, which removes the risk of a single high-temperature event shutting down the entire array. Whatever hardware you choose, protecting your inverters from direct UV radiation is essential if you want the system to operate through the hottest hours of the day. The final environmental hurdle for desert solar is baked-on dust and sand. When panels get dirty, homeowners often reach for a garden hose. In a high-heat environment, spraying standard hard tap water onto a hot panel is a mistake. The water flashes into steam, leaving mineral deposits baked into the glass. These deposits create hot spots that can permanently damage the silicon cells, dropping your overall power output by up to 15%. Protecting high-efficiency hardware requires maintenance. That means scheduling professional cleanings, using specialized deionized water systems during the cool, early morning hours. Sorting these specs comes down to matching hardware to your climate and budget. Looking at this flowchart, if you live in a mild or cold climate, like the Pacific Northwest or Northern Europe, standard TOPCon panels on normal racking are sufficient. Paying the HJT premium in those regions won't provide a significant additional return. If you face extreme heat but have a strict budget, the best path is standard TOPCon panels, but you must pair them with a 5-inch mounting gap and a shaded north wall string inverter. If you live in extreme heat and want the highest possible yield, you need premium HJT bifacial panels paired with microinverters and elevated rail mounting. Matching your hardware to your specific coordinates prevents you from overspending on tech you don't need, or watching your production numbers sag just as your utility rates peak. The final hurdle is managing the installation company. You need to ensure they don't apply templated practices to your specific environment. Before you sign any contract, explicitly demand that the contractor writes the temperature coefficient of the quoted panels directly into the proposal. Next, have them document the specific airflow and mounting clearance plan. You want that 4 to 6 inch gap confirmed in writing. If an installer is unwilling to adjust their standard mounting practices for extreme heat, they should be disqualified from the bidding process. In extreme heat, the highest rated panel on the market is still at the mercy of the mounting plan and the airflow beneath it. Proper installation is what determines the actual